This video is going to help you with finding what's called simplest form. Basically, it comes down to simplifying radical expression statements. And when we're talking about radical expressions, we're basically talking about fractional exponents or rational exponent expressions. Sometimes it's easier to look at it as a radical, sometimes as a rational exponent. But if we're going to be dealing with fractions, we also want to remind ourselves of the two big operations we do with fractions. With fractions, you can add two fractions as long as you have a common denominator. So if I'm looking at 1/2 and 1/4, one way to add those fractions would be to make this 2 into a 4. So I'm going to multiply the bottom by 2, at the same time multiplying the top by 2, essentially multiplying 1/2 by 1, 2/2. So that becomes a 2/4 plus 1/4 equals 3/4. Now, the idea like that can help you if you're multiplying two expressions with equal bases. Remember, if you're multiplying with equal bases, you can essentially add your exponents. And in that case, 1/2 plus 1/4, as we just found out, is 5 to the 3/4, and that is a fairly simplified expression. Now, you can't do that when you don't have equal bases, but if you're multiplying exponents, such as here where we'd want to maybe do power to a power, remember two things multiplied both to the same power, you can say that 2 to the 4th is to the negative 1/4. At the same time, 3 to the 4th is to the negative 1/4. Well, we can multiply our exponents then. And when you're multiplying fractions, remember, you're just going to multiply the tops. So negative 4 times 1 is negative 4. And multiply the bottom, or the denominators. 1 times 4 being 4. So that comes out to a negative 1. So 2 to the 4th to the negative 4 is really 2 to the negative 1st times 3 to the 4 to the negative 4, 3 also to the negative 1, which makes this a 1/2 times a 1/3. And again, if you're multiplying your fractions, 1 on the top, 2 times 3 is 6 on the bottom, and your answer is a 1/6. That same idea could help you out with this expression, or that same idea of at least sort of distributing your exponent. If both of these two things multiplied are to the same power, so we can separate them, well, two things divided to the same power means that I could actually pull that power out of there. We could actually say this is 12/4 both to the 1/3, sort of using that idea backwards. And power to a power says we're now to the 2/3, but 12 divided by 4 also says that this is just a 3. So if I want to simplify that expression, basically I'd be taking the third root of 3 squared, which would be another way of writing our expression here. But we can leave that as 3 to the 2/3 power. Now, when we're finding simplest form, basically it comes down to four main ideas. Number one, we don't want any negative exponents left in our final answers, similar to the problem we just did in the middle of the screen on the last screen, where we had those negative 2 to the negative 1, 3 to the negative 1. One of the things we need to do is get rid of those negative powers. We also want no parentheses left in our final answers. If we can get rid of parentheses, we want to do that. The big idea is going to be part C here. We want to reduce any radicals and radicands. So anything that's too large underneath the radical, we want to break down and try to pull out from underneath that radical. Or if we can simplify our radical, note that here you see a 6 and you see a 4th power. That means this is really x to the 4/6. Well, remember, 4/6 is really 2/3. So we've reduced the 4 down to a 2, the 6 down to a 3, or essentially the index went from being a 6 to being a third root of x squared. And that is a reduced radical. Reducing the radicand comes more down to breaking them down. 54 is really 27 times 2, and 27 is a 3 and a 9, 9 being another couple of 3's. And since we're doing a third root, we're looking for a set of 3 things. So 1, 2, 3 3's is a solid 3 outside of my root, and that leftover 2, remember, gets left underneath. Or if you think about it, if you have a big party, these 3's, that party of 3's, gets to go outside. They get to go to the meal, but the leftovers get put back in the fridge. Always my great way of thinking of, or what I think is a great way of thinking of what to do with those numbers. Now, if you have a fraction, that comes down to our fourth rule here. And we can first say, well, roots, remember, of fractions, we can say the fifth root of 3 divided by the fifth root of 4. The problem is there's really not much I can do with those. The big thing we don't like is that I don't like radicals in the denominator. So I'm going to make this into a fifth root of 2 squared. Remember, 2 squared is the same thing as 4. But if I can break that to prime, that's going to help me out. Because what I want to do is complete this. I want to make this into a set of 5 so that I could reduce or break down that radical. Well, if you need a set of 5 and you have 2 squared already, basically I need a 2 to the third. 2 plus 3 then would be 2 to the fifth. But remember, if that's going to be a 2 to the third, it also needs to be under a fifth root. So let's go ahead and do a 2 to the third fifth root on top as well. That way it becomes the fifth root of 3 times 2 to the third over the fifth root of 2 to the fifth. Well, there's no sets of 5 on the top, and remember that when we're simplifying, no decimals. Do not go trying to find any of these numbers. If they don't come out to a nice number, we're not going to mess with them. But 2 to the third is 8 times 3 is 24. So the fifth root of 24 in the numerator is a perfectly fine expression. On the bottom of my fraction, notice, fifth root, fifth power, that just becomes a 2. At least I don't have any radicals in the denominator. We want to do what is called rationalizing the denominator. No roots in the denominator. That's rationalizing the denominator. Now, on the next couple of pages, I just have a bunch of examples for you. So go ahead and write down these examples. Try simplifying them. Remember, no decimals. And see what you come up with. And if you pause the video now, I'll have the answers up for you in just a few seconds. All right, here are those examples for you. In the first one, remember, you're just multiplying the bases, so add your exponents. 1/4 plus 3/4 is 3 to the first power. Remember, 3 is still your base, so even though you got 1 up in the exponent, that's 3 to the first. Over here to the right, I just went ahead and said, well, hey, they're both equal roots, and if we have equal roots multiplied, we can multiply what's underneath. 16 times 4 is 64. Then if we break it down looking for sets of 3, well, it can basically become a set of 6 2's, or 2 to the third times 2 to the third. Third root of each of those is 2, and 2 times 2 is 4. You could have set that one up a few different ways, but the big idea is, did you come up with 4 for a final answer? The fourth root of 16 divided by the fourth root of 81 is what the bottom lower left expression is equal to. And the nice part is, fourth root of 16 is 2. And even though there's a root on the bottom, the fourth root of 81 is just a clean 3. Not a lot of extra work there. And the last one, the third root of 1 is 1, but the third root of 4, unfortunately, is not a nice number. So if we take 4 and break it up into its primes, 2 squared, basically I need another 2 to make that a set of 3, to make it a clean 2 on the bottom. So I put a third root of 2 on the bottom and a third root of 2 on the top. 1 times the third root of 2 stays third root of 2 on the top. And the third root of 2 squared times third root of 2 to the first basically becomes the third root of 2 to the third on the bottom. And remember that roots cancel powers, and you just get a clean 2 on the bottom. Here's another page. All of those ones were just with numbers. You could have checked all of those in your calculator more than likely. Make sure the decimal of the beginning statement, such as 3 to the fourth times 3 to the negative, or 3 to the 3/4, comes out to 3. Or on the bottom especially, the third root of 1/4 should have the same decimal value as the third root of 2 divided by 2. If they come out equal, then you know that all the steps you took worked. Now with variables, however, you won't be able to check them on your calculator, so you need to be confident that you're using the correct steps. Go ahead and copy these examples down. Again, I'll give it a little bit of time. You can pause the video, and then you can bring up the answers. All right, all the answers are up for you. The first few are fairly simple exponent rules. Again, add your exponents, becomes 6/3, but 6/3, remember, is 2. Power to a power we multiply, but 3 over 6 is a 1/2. And you could either leave that as y to the 1/2 or convert it to the square root of y. Either one of those is a perfectly good answer. If you have two things multiplied under a root, you can break that into two parts. So the square root of 4 becomes 2, but the square root of a to the 6th, basically 6 divided by the index of 2, becomes a 3. So that's a to the 3rd. Down here to the lower left, again, same idea. I broke up my division into two separate roots, made them into fractional exponents, and then reduced those exponents to give me my final answer. The last one, again, is the one that requires the most work. B to the negative 1/3. And then negative exponents make reciprocals, so 1 over b to the 3rd. But b to the 1/3, remember, is a third root. And in order to make that a nice whole number exponent so that we don't have a root in the denominator, well, one way to do it is think about adding those exponents again, like we did in the upper left. What would you add to a 1/3 to make it a whole number? Well, 2/3, of course. So 1/3 plus 2/3 becomes b to the first power. But if I multiply a b to the 2/3 in the bottom, you also have to do that on top, up in the numerator. So b to the 2/3 on top divided by b to the first power on the bottom. That's the cleanest answer you're going to get. Again, simplest form is not always easy. You got to work with exponent rules, reducing radicals, doing a lot of steps. But just be careful, take it one step at a time, and good luck.